Okay, so hello everyone. Welcome to Quantum Conversations number 9. Today we're going to talk about the relationship of industry and academia, particularly focusing on quantum finance, both theory and practice. So I am Mert, and I'm Mert Sanjan. I just graduated from Stanford, my master's. For my undergrad, I was also at Stanford. I did a double major in physics and symbolic systems. For my master's, I focused on management science and engineering. I was a teaching assistant for the quantum computing course offered on campus. And I've been working closely with the Stanford Quantum Computing Association. I led the committee, the partnerships committee there for a bit. Now Yosh leads the partnerships committee. So Yosh, do you want to introduce yourself?
Yeah. Hi, everyone. My name is Yosh. I'm a third year at Stanford, currently majoring in physics and prospectively double majoring in math. Yeah, I'm the partners and committee or partners and events committee lead right now. And yeah, I'm glad that everybody's here and showing an interest in quantum computing.
Yeah, so for our main speaker today, we're going to have Dmitriy Chermoshentsev. If I'm not butchering your name, Dmitry.
Good.
And Dmitry works on a very cool project on using quantum techniques to optimize portfolios. He's working on real world cases right now. So we're going to focus on that. And this is going to be very informal. We also have Professor Ming-Shi Kim participating as well. He will be in the audience and he will chip in from time to time. Professor Kim is a chair of the Theoretical Quantum Information Sciences at Imperial University. His main research is not in quantum finance, but he's interested in quantum finance. And he holds an MBA as well. So he has worked on options pricing before. So today I would like to be very, very informal. And so it will be very much discussion based. Usually people who have participated in our sessions know that we are more on the informal side where people talk all the time. It's very much discussion based. So this is not like a presentation. It's more like a talk of friends. So it would be great if we went around quickly and asked everyone to introduce themselves. So it would be great if people are available, they would open their cameras on and maybe give like a 5-minute introduction. So Dmitry, can we do that first before the presentation, if that's fine?
Yes, of course. My name is Dmitriy Chermoshentsev. Yeah. Do you hear me?
Yes, sorry.
Okay. Okay, let's start. Yes, we can start now. Yes.
Yeah, we can hear you.
Okay. Hello, dear colleagues. My name is Dmitriy Chermoshentsev. I'm a PhD student at Skoltech. It's a Skolkovo Institute of Science and Technology in Russia. And also I'm a researcher in the Quantum Optics Group or the Russian Quantum Center. My scientific advisor is Alexander Lvorsky, who is a professor at the University of Oxford. And today I'd like to provide a general talk about some part of our research projects in the area of optimization by quantum adiabatic and quantum inspired algorithms in different tasks, especially in portfolio optimization. Okay, just a moment.
Okay, thank you.
Yeah.
And yeah, can we do the introductions of the participants as well, just for like 5 minutes before we delve into the
Yes,
presentation?
yes, of course.
Okay. So Yosh already introduced himself. Logan, you have been coming to our sessions a lot, and we would love to hear about you as well. Okay, let's go to Jamie.
All right, hey Mert. I'm Jamie, taking classes at Stanford this quarter, and next fall I'll be in graduate school of quantum computing at Wisconsin-Madison.
And we have Nathan. Hi, Nathan.
Hi, So I'm a retired guy who's always been interested in math and physics, and finally realized it's time to do something about it. So 3 years ago, when quantum was coming out, it was a good, it very much appealed to me because it intersects both those fields. And plus it's a lot of philosophy too, which is what I majored in when 50 years ago when I was in college, which is probably twice the time that the average age of the person on this conversation is. Anyway, so I've been doing a lot of studying and self-studying, and it's coming along well. And I put together a site called Quantum Curious, and I'm hoping to show you at the end for 5 minutes. It's very good for beginners, and get some feedback from you guys about it. But I very much like these sessions, the interactive part.
Yeah, thanks, Nathan. Yeah, Nathan's website is amazing. I would highly suggest checking that out if you want to learn more about quantum computing. Chi-Chun Qian, hello.
Hi, so this is Chi-Chun Qian. I'm an associate professor in physics at UC Merced, so the new campus of the UC system. And I work on theoretical atomic and molecular physics, but I'm also interested in, say, applications in quantum computation. So good to see everyone.
Cool, nice to meet you. Logan, I see your video is on now. Do you want to say a few words about yourself?
Yeah, sure. I'm Logan. I'm a freshman, and I'm prospective math/CS major, but I'm really interested in quantum algorithms, especially like applications to cryptography.
Great, great. Let's see. I'm trying to find people who have already their videos on. Alexei is driving. He's gonna, when he has a better connection, he will join us. Oh, Brett, nice to see you again. If you want to say a few, Brett Cones, if you want to say a few words about yourself as well. We were here before.
Hello, my name is Brett Kuntz. I'm from Missouri in the Midwest. I did a talk a couple months back with you all, and yeah, I think this is just a really interesting up and coming field in general. So.
Thanks. Chris Sell. So it's our tradition to cold call people. I'm sorry if you don't want to like introduce yourself, that's fine. But I'm just gonna keep on cold calling who has their videos off.
Yeah, no problem. Hi everyone. I'm a postdoc in Ming-Shik's group at Imperial. I work on variational quantum algorithms, quantum simulation, trying to run quantum algorithms on real IBM hardware.
All right. Thanks, Chris. Tobias Howe.
Hi, I'm Tobias. So I'm sorry. Okay, so I'm Tobias. I'm a postdoc at Ming-Shik Group. Before I was a PhD student in Singapore, as well as I used to work at Entropica Labs, a quantum computing startup. So pretty much I work on anything related to quantum computing. Recently, with some colleagues, we also wrote a review on this quantum computing, which may be interesting for you to read.
Yes, it's interesting to all of us, I think, who are in the session.
You will send it around the chat. Thank you.
Shreya Kumar.
Hi. Hey everyone, I'm Shreya. Clearly, I'm underprepared for this time, but I came to know of this quantum initiative because of the coding school, which is where I'm doing sort of like a course on introduction to quantum computing. And I'm particularly interested in quantum cryptography and quantum communication. And I'm probably going to start with a internship or like a research program after August. So that's why I'm here. And I'm from Bangalore, India. Yeah.
Amazing. It's kind of late there, I guess, or early. I'm so confused about time.
9 p.m.
Okay, it's okay. Matt, my namesake. Mert karşılayalım.
Hello everyone. I am from Turkey. I am currently undergraduate student at Eskişehir Osman Gazi University. My department is mathematics and computer science. Also, I'm associated with a community on Turkey. It's named Turkey, who works on quantum computation. So also that's okay, I think.
Yeah, thanks for sharing, Mert. Yeah, Q Turkey, we've been working closely with them. Q World actually is the larger organization, so they have a lot of branches around the world. Zibo Yang.
Hi, I'm a graduate student in UC Berkeley, and my advisor is Brigitte Whaley. Just have a general interest in all like branches of quantum computing, and my advisors forwarded your like email, and I'm curious to see what's in finance.
Yeah, so Stanford Quantum has been partnering a lot with the Berkeley Quantum Computing Club. I don't know if you're involved with them, but they're great.
Yeah, I've been to several of their like talks. Yeah, they are doing good things.
Yeah, when I was at Stanford, we organized the chess tournament, and Berkeley was the Berkeley finalist was against the Stanford finalist for the final game, and Berkeley won, unfortunately. And there's another one coming up. I think Yosh, we could talk about that after the meeting. So Cody Guggen.
Hi, I'm a student at University of Chicago, and I'm just interested in learning more about quantum computing and like its application in finance.
Thank you. Augusto Kialbovics.
Oh, hi. How are you?
Hi.
I'm.
Oh, nice to see you again. Sorry, I've been seeing you around.
Yeah. No worry. Yeah, I attended a few meetings last year. I missed the ones on the start of this year, but I'm located on Buenos Aires, Argentina. I did a master on physics, but now I work as a software engineer in a finance risk-related company. So I'm trying to stay up with the quantum things a little bit by checking the meetings a few times, but I'm mainly doing that for now.
Yeah, thanks for joining. I think Sarah has low bandwidth issues. That's what I read on the chat. Yeah, she's a MIT junior year, and her major is math and CS. Okay. Same with AB. You can, so his short intro is he's in biomedicine or she is in biomedicine, or yeah. I can't understand a lot from the text. I have sorry, it's very small. I have taken introductory course in quantum computing here in Helsinki. I am very keen to learn more about different fields in quantum computing application side, where it's likely to find an application in the foreseeable future, and very happy to be here with you today. Okay. Great. S. Chan, did we already go to? Yeah, sorry, we did already.
Okay. I'm a VC, venture capital. I just want to learn a little bit about this thing. Thanks.
Yeah, thank you. We have Ali Lopez here as well. Okay, David Nisi.
Hey, I'm David Neese, and I'm a freshman at Stanford. I'm prospective major in physics and philosophy. Philosophy is actually almost kind of my primary interest, but I really like physics, and I also like finance, and this seemed like a kind of a cool little intersection. So I'm mostly here to just listen.
Amazing. A lot of people from Stanford today. William Wang. Okay, and then lastly, Vasily Nachev.
Oh, hello. I'm a software engineer from Los Angeles. Just interested in current state of quantum development, and yeah, just staying tuned.
Okay, so now that everyone had their intros, we can go ahead and start, but please chip in at any time. If you have a question, shout it out. Again, we're very informal. Let's keep this as a discussion, please. And yeah, so we can go ahead with Dmitry. Thanks for waiting, Dmitry.
Okay. Yeah. And I want to start my presentation with a brief description of our organization. That's the Russian Quantum Center, RQC. RQC is a private research organization in Russia that specialized in fundamental research in quantum physics. Currently, there are 17 scientific groups that cover, I think, all areas of quantum physics. Since we are a non-state company, we need to look for a private investment and launch our own commercial projects. Thus, now the Russian Quantum Center has launched 8 spin-off companies engaged in developing commercialization devices and technologies designed in the RQC scientific groups. More detailed information about our center you can find in our site. Okay, let's go further. And currently, our scientific group investigations are mainly focused on the problems that the adiabatic annealing approach can solve. Let's talk about the quantum annealing and about the practical tasks that this annealing can solve. What is the meaning of the annealing process? Adiabatic annealing is a general approach for solving optimization problems from a wide class. In the process of annealing, we optimize the sum cost function. And the most famous example where annealing is used is a problem of unconstrained binary optimization, or quadratic unconstrained binary optimization, which called cube. Here we want to optimize the polynomial function on the binary sequence of zeros and ones, but in physical devices, we operate not with zeros and ones, we operate with spins, and the values of these spins is plus or minus 1. Therefore, we should reformulate our initial problem in the Ising model formalism and finally optimize the Ising energy. Yeah. Please note that our quantum annealing is different from the annealing in, for example, metallurgy. In metallurgy, people used it for stress release in some materials and homogenization for better mechanical properties. Okay, let's go further. The most famous commercial company that realizes the process of quantum annealing is D-Wave Systems. Their devices operate with superconducting loops that play the role of quantum qubits. And the annealing process in D-Wave is described by the following Hamiltonian. You can see that this Hamiltonian is the sum of two terms, the initial Hamiltonian and the final Hamiltonian. Let's consider the first term. And the lowest energy state of this initial Hamiltonian is when all qubits are in a superposition state of zeros and ones. This term is also called the tunneling Hamiltonian. And if we consider the second term, the final Hamiltonian, the lowest energy state of the final Hamiltonian is the answer of the problem that we are trying to solve. The final state is a classical state and includes the qubit biases and the couplings between qubits. This term is also called the problem Hamiltonian. In quantum annealing, the system begins in the lowest energy state, eigenstate of the initial Hamiltonian, and as it anneals, it introduces the problem Hamiltonian, which contains the biases and couplers, and it reduces the influence of the initial Hamiltonian. You can see it from this graph. We reduced the coefficient A before the initial Hamiltonian and increased the coefficient B. As a result, at the end of the anneal, it is the system state, it is the ideal state or the problem Hamiltonian. Okay. Okay, let's talk about the practical applications of the annealing. Many practical tasks in real life can be transformed into the Ising model formalism. It is, for example, combinatorial optimization tasks, traveling salesman problems, portfolio optimization, plotting, folding, investigation of the energy structure of molecules, etc. In general, such problems are NP-hard. As a result, problems with large sizes cannot be solved by classical determined approaches in satisfactory time. That means in large sizes, we face with the effect of combinatorial explosion. But in practice, we almost every time face and work with large problems, and we want to have a possibility to obtain good enough solutions for these problems. And the new generation of special purpose devices like D-Wave will help us to get such answers. And the special purpose device that we investigate in our group, it's based on optics and called coherent Ising machine. Today, we will not precisely describe the device technical aspects, but let's try to understand the main idea of this device briefly. The main element of coherent Ising machine is a nonlinear crystal where the process of parametric down conversion could be realized. We use the pump, you can see here, and if we are working the regime when we work below the oscillation threshold, we can generate that squeeze state of the light in our nonlinear crystal. But if we want to work above the oscillation threshold, we can generate the incoherent mixture of two components with the phase 0 and 5, for example. Yeah. And what is the structure of the real coherent Ising machine? The real coherent Ising machine proposed by Nagaki et al. This nonlinear amplifier, squeezer, is placed inside the fiber loop. Just a moment, I find the ticker. Laser. Yeah, okay. Inside the fiber loop. And we measure, inside this loop, the sequence of light pulses circulate. We measure the quadrature xi of each pulse, exciting the amplifier, and then apply the displacement operator on amplitude to each gth pulse. Yeah, which enter in the amplifier. Then we start with all pulses in a vacuum state and repeat this procedure for 100 or 1000 loops. And finally, the resulting amplified pulse sequence will have phases corresponding to the minimum of the Ising Hamiltonian. And the question why we have the phases that corresponds to the ground state of our Hamiltonian. The answer is the following. We can see that the displacement amplitude that we apply to our pulses plays the role of the gradient for this Hamiltonian. And as a result, our displacement pushes the spin toward energy minimum, pushes the phase. Let me note that here spins are approximated by a continuous variable because we work with the laser pulses, not with spins. Okay. And now we come to the next part of my presentation devoted to the quantum-inspired algorithm SimCIM, because it's a simulating of coherent Ising machine. This algorithm we developed in Russian Quantum Center, and it simulates the process of optimization in real coherent Ising machine, but on the classical computer. Moreover, we showed that it is possible to achieve the same performance in terms of computational time as a real device by using GPU. Yeah. After the detailed investigations of fiber coherentizing machine that we saw in previous slides, we understand that quantum effects do not play a significant role in the optimization process. As a result, we can neglect such a quantum nature of the device and realize the classical optimization algorithm on the computer. In our consideration, we treat each amplitude in our coherentizing machine as a real value and replace two photon losses by linear constraint. You can see it here. And finally, our evolution simplifies and have the following form that you can see here. So just a simple step of our algorithm. Then we benchmark our algorithm on different graphs, on different tasks, and if you want, you can find the results in our paper. Okay. Then we apply our algorithm to different tasks like protein folding, like quantum chemistry tasks, but we find that the most important and prospective task is portfolio optimization. Okay, to solve this problem, we use the following scheme. We take the historical data about asset prices and use the equally weighted markets model to transform this data into the Cuba problem. Then we convert our data into the Eisen-Hamiltonian formalism and start to optimize by our quantum spite algorithm SimCIM. Let me know that we fix the number of assets in the portfolio as M. It's a number of assets in our portfolio, and by using the penalty parameter lambda. And also we vary parameter alpha to investigate the effective portfolio frontier, which is one of the most important parts of the markets optimization, to find the optimal portfolio by investigation the optimal effective frontier. Yeah. And unfortunately, due to non-disclosure agreement with our colleagues from Central Credit Bank, I can't provide a very precise and very detailed information about our strategy, but I can show the performance. And we developed with our colleagues a strategy based on the application of SimCIM algorithm enhanced by machine learning techniques. Yes, in such project, we collaborate with our colleagues from Central Credit Bank, supporting us and advising about strategy improvement from the financial point of view. We analyzed our strategy over the 25 years period of time and finally investigated that it shows excellent performance in terms of annual returns. Yeah, our strategy is the first strategy here and here. And we investigate that our model is very good in terms of annual returns, in terms of Sharpe ratio, and in terms of maximum drawdown. Our analysis shows that this Sharpe ratio, the developed strategy, is comparable with the Sharpe ratio obtained by the resample efficient frontier technique with a good classical approach to that used in this area. Still, the average annual returns in our model are much higher than in resampled efficient frontier. You can see it from the first graph, if compare the first and the third column. And moreover, our strategy has the best performance in terms of the maximum drawdowns. It means that in all period of 25 years, we in one time lost only about 35% of our capital in one time, but all other strategies lost more. Yeah.
What's your time frame for that? Is that a yearly loss or a monthly loss for the drawdown?
For drawdown, no, we consider the maximum drawdown through all 25 years period.
Okay, perfect. That's
in
fine.
1 month, yeah. But but we buy and sell the assets every 1 month, every month. Yeah.
Okay.
But consider all the period of 25 years. And I think that's the result of crisis in 2008. Yes, I remember. That's
okay.
Yeah. And yes, in this slide you can see the monthly and annual distributions of returns. Here there's a heat color map, a heat map, and here you can see the annual returns distribution per year. Yeah, and you can see that the most crucial crisis was in 2008. And in this two graphs, you can see distribution, the histogram of monthly returns distribution and distribution relative to the S&P 500 equal weight. Yeah, and we can see that because we work in the equal weighted model, we use equal weights for all companies in our portfolio, and as a result, we should compare it with the equal weighted models. It's more precisely, I think. And you can see that we also better in mean value, and generally we better than the S&P. Yeah, and I think that's all for our research in portfolio optimization. And if you have any question, I will be happy to answer them.
Yeah, I have a quick one, Dmitry. Nathan here. Maybe you mentioned it or I missed it. So on this graph you're showing now, how is this different or more beneficial to your clients than the classical approach they're using now to address some of these issues?
Yeah. We find that our approach have a very huge returns in comparison with the classical, for example, technique like Markowitz or the sample efficient frontier. That's why it's good to use our optimization strategy. If you want to have a high returns with comparable volatility, you can use our model. But
so on this graph now, how can I confirm that by looking at this graph? These are your results. They're not comparing to classical results, if you understand my question.
What you mean in classical results?
I mean, if they didn't have this approach, they'd have certain results. And you're making this interesting claim that your approach is an improvement. How much of an improvement? Or
the main idea why we can use this algorithm and why it's benefit for us, because we work the computational time of our algorithm is very small. It's about 2 milliseconds per one optimization form, and as a result we can test a lot of strategies in a very short time period, and then we can understand what is the best parameters for our model and what is the worst parameters, and take the better one. In comparison with classical approaches, you mean the classical approaches from finance, or you mean classical approaches for binary optimization algorithm?
In general, just in finance. So you're saying this took, I didn't quite hear you, 2 milliseconds or something to that effect? How long would it have taken if one used conventional techniques?
Maybe. Actually, I think it strongly depends on the algorithm that you use. We compare our results with Gurobi performance, and Gurobi is comparable with our approach, and I think sometimes it's better.
Okay,
but
thanks.
yeah,
That's
but
helpful. Thank you.
Dmitry, thank you for your talk. For me to understand what you're doing, can you go back to the mapping part? So you had a slide to show how you use your computer. So is it the next one? So there was a price, and then there was a model. Is it this or the next one?
yeah, that's the equal-weighted model, and the first term is the covariance part of our quadratic form. The second part corresponds to the returns of our model. Yeah, and the last one is
so what is Q here
on the side. What?
What is Q? So is it Q is
Q
your price?
Q here is the binary variable which can have only two values, 0 or 1, and we want to understand what the companies we should to buy. It means that we have the 1 as a result value of the variable for this company, or 0 if we don't buy the company. Yes, and this just the weights of the company in our portfolio. Yeah.
If I'm not mistaken, Dmitry, this is in terms of physics, this is very similar to an Ising model where the these are the spins, right? And then a 0 is actually like a -1 in terms of an Ising model, a down spin, and then 1 is an up spin. And why this is practical is that you convert an Ising model into a portfolio optimization problem, and the spins tell you either to buy or not buy the stocks.
Yeah, absolutely. Yeah, that's right.
But then it's still not very clear to me how this helps your portfolio, because Can you show the next slide, or there was another slide? No, not this one.
Yes.
No, before then.
I think it was the one before with the annealing model, Dmitry. The one before.
Yes.
I think it was even before SimCIM.
I think it's fine. Yeah, probably it's my mistake that I don't remember which slide it was. So you're mapping your portfolio into the Ising model, but I still share the view. I mean, share the same question as Nathan. I don't see how quantum computer helps you, because it. I mean, do you use like coherence properties at all, or?
Okay. And the answer is the following: we work with discrete variables, and as a result, there's a problem also in p-hard. And if we will work with a huge, with a very large universe, when we try to optimize not, for example, 500 companies, but 500,000 companies, we should use the devices like D-Wave or coherent Ising machine, because the classical approach is not very effective, and they effective for not a very large quadratic forms, and as a result, this quantum annealing increase the time and increase the quality of the final solution that we can obtain. Here we consider only the 500 spin models, because we're working with the S&P 500 universe, but practically we can extend it into large sizes. And for large sizes, the quantum devices, quantum adiabatic annealing devices like the wave will be very useful. Yeah. Now we just in the first step of the investigations of the performance of this quantum diabatic annealing devices in different problems, and one of these problems is the portfolio optimization, and we find that that coherent Ising machine will be very effective in this problem. So yes.
Okay.
I have a question also. Have you tested this sort of model in maybe less bullish financial environments? Like, I mean, there was like the 2008 crash and then the one in last year. But there's been a pretty steady uptrend since like the 70s in US markets. And I'm wondering if the same sort of thing could be applied to something like the Nikkei index, where the Japanese market's just kind of like going up and down over the last however many decades.
Yeah, we consider the period from 95 year to 2021. Yeah, that's the period, but we test only on the USA market and only for the S&P 500 market, S&P 500 universe.
Yeah, that's a very interesting question, Logan. Actually, I've been thinking about that as well, because as we saw, there's a drawdown in 2008, as expected. And it would be interesting to look at a model where shorting is allowed so that you can also have negative weights. And it's very hard to do it in this setting because we only have two spins that we can use. It's either up or down, which means you either buy a stock or not buy a stock. And there are techniques around that. Maybe you limit yourself to either only buying and shorting, and that would allow you to maybe be more hedged against a more volatile market. There are other techniques to increase your weights, but the thing here is that we're working with NP hard problems, which are discrete weights, and the Ising model inherently allows for two selections. But that's a very good question. I think, Dmitry, that's a very interesting test to do. Maybe test your model at a more volatile market or even a bearish market.
Yes. Yes.
Okay, thank you.
So have you looked at any shorting models at all, Dmitry?
What do you mean,
Or
shorting in time period?
Shorting, I mean, like maybe negative weights. Only make, for example, only short portfolio.
No. As I told, we just start this project, and unfortunately, we haven't got enough people and time to test all possible configurations and tasks. Yes.
I mean, it's a fascinating area to look into, I think, because there's so much data available in the financial markets, and it's very well tracked because people care about money. So there's a lot of data to work with. And here there's a distinction that we have to make as well. So right now Dmitry is describing a solution inspired from a quantum device, but working on a classical computer. So maybe we could talk a bit about the coherent Ising machines themselves, the hardware. And when do you think a coherent Ising machine would be not scalable, but even like allowing for the test of an algorithm like this?
Yeah, a few words about coherentizing machines. These devices are very scalable because our Japanese colleagues use fast FPGA. It means that create the displacement by the electronic device, and as I remember now, they scale their machine up to the 20,000 of variables, and it's a very huge device. Also, as I remember, they compare the performance of coherentizing machine with the D-Wave 2000Q, and show that SIM significantly outperformed the D-Wave in the dense graph, but the performance is comparable on the sparse matrices. Another good point for SIM that they can realize fully connected graphs, and they can connect all variables inside this machine. But in the wave, we know that we can use for 2000Q, or we can solve only problems with the size of 64, as I remember, qubits, not larger. Yeah, and this is another performance. This is another advantage of SIM, that they can scale and solve fully dense, fully connected NP-hard qubit problems. Yeah.
Perfect. Yeah, I work with D-Wave machines a bit, and it is very important to, like, it's very impressive that these machines have all-to-all connectivity, because D-Wave machines have constrained connectivity. For example, a 500 variable problem becomes 1600, 1700 qubit problem in the actual machine, because you have to embed it. So all-to-all connectivity is very important for financial applications.
Yes, yes.
So do we have any other technical questions? Otherwise, I want to take the discussion to a different level. But this is a fascinating topic, so please shoot if you have any.
I've just got a small question. So forgive me, I don't really have too great of a knowledge in finance or physics. So if this question was already answered, sorry for that. But to my understanding, the Markovits model is part of modern portfolio theory, which is one way of sort of doing portfolio optimization problems. But I'm wondering how generalizable the solution is. So for example, like it seems like the way this works now is that you've discovered some similarities between this Ising model and the Markovits model, but people have, some complaints about the Markovits model and how it evaluates risk, for example. So if somebody were to create a new model, would you still be able to use the same techniques here in order to take that classical model and put it into a quantum system where you have more computational power? Or is this like, does this only work in response to the Markovits model?
Yeah. Of course, we started this project because we also developed the coherentizing machine in Russian Quantum Center, and we plan further use these devices that we develop. We will develop for practical tasks, and initially this consideration was devoted to mapping of data to quantum inspired or real quantum device. But here we use the classical computer to optimization, and I think that this research mostly related the performance of coherentizing machine to solve the financial problems. Here we consider the Markovits model, but of course we collaborate with our colleagues from banks, and they give an advices how we can transform our model to more appropriate way and to improve how we can improve our model from the financial point of view, and how we can change the model. Yeah, and I think that's partially about the Markowitz model, but partially about the usage of quantum and quantum inspired algorithms on this class of problems. Yes.
All right, thanks.
Yeah, I think that's also a very valid question, because
I'm sorry, just maybe let me know, please, that these results, it's not only the classical Markowitz approach. We also use some techniques that we get from our financial colleagues, but unfortunately I cannot tell about this these features now. Maybe we publish a paper, maybe we won't do this. Unfortunately, I don't know, but now I have a non-disclosure agreement. I cannot tell.
Yeah. So yeah, I mean, David, this is a so the Markowitz model came up in like the 50s, I think. So it's a very old model. It's based on a highly optimistic assumption that according to capital asset pricing model, the prices of the assets in an efficient market are the actual prices. So, but we've seen over the years that doesn't really work in practice. So, but it is a very good base for approximating prices, and actually not approximating prices, but maximizing returns and minimizing risk in some level if you have other parameters like Dmitriy is using and not able to disclose. And it is very lucky that it fits the Ising model very well. So that's why people in quantum research are actually focusing on it and using it as a base to optimize portfolios. But there's always another term usually that's used in practice. It's either a penalty term, a concentration term, something that actually makes the model fit into the real world data. And following that, Dmitry, so the way you use the Markowitz part of your model, the way you calculate returns and risks, that's based on historical data, and that's purely deterministic, right? You don't use any risk models that actually forecast into the future. You create your covariance matrix and everything through the historical data, right?
Yes.
Okay. So again, yeah, this is like pure Markowitz in that side then, but there are many more techniques, and to have this returns is these returns so early in the modeling part is very I think impressive. Okay, any more questions for the technical side?
I think we can generally discuss about the usage of quantum computing in financial area. Maybe we can find some other interesting tasks, not only portfolio optimization. Yeah, there are many tasks. I think that people are trying to do. There is the vehicle rerouting problem, is very famous, and inventory management also very famous. So optimization problems are all over the industry, which brings us back to our topic where research and industry meet. So I think this is a very exciting field, because in quantum computing, there has to be a collaboration between industry and in academia. It is a very capital heavy research area, because it's very expensive to build quantum computers. And it's also very beneficial for the industry to have these very powerful machines, theoretically powerful machines that are proposed to have real world use cases, as we see with Dmitry here.
So maybe Dmitry, you can talk about your experience as a researcher, how you communicate with people from the industry, how your role shifts throughout the day from a person who's doing pure research with academics and then a person who's talking to financial advisors. And so how's that for you in a day-to-day basis?
Yeah, okay, now the quantum technologies is very, very important and very popular from the industry. And I think in the last 2 years, that's not so complicated to talk with people from financial sector or for example, oil engineering companies and something else. The main problem, I think, is to find the same language with these guys, because we, as a scientist, we talk about the high materials and high matters, and sometimes it's very complicated to tell your ideas to the guys from the financial sector, for example, from the banks, and you should to understand how you can change your language when you communicate with these people, and then it will be success, I think. This will be successful.
Yeah. What do people think? So most of us here, I think, are part of university or academia, but if anyone is just more in the industry side, can someone talk about that experience?
I think I can shut down the presentation, yes?
Yeah. Well, I guess I can talk about my experience, but I've been in industry for the last few months, and my role is very research based. So it's been like this since the last 2 companies I've been in. But from what I see in my organizations is that organizations like this Quantum Conversations or Stanford Quantum Computing Association, where we don't have this division between industry or university anymore. Everyone is interested in learning more who are in quantum computing, because we are all students. It's a field that changes every day. Every day there's a new idea and another idea gets demolished. So it's very fast. So everyone is listening to each other, and it's a great field that brings all of these different parts. We have national labs, we have universities, and we have people who have other motivations for their own organization, like increasing profits. But we are all combined with the same goal, which is advancing the field, because it serves everyone. That's why we see everyone coming together from even different parts of the world. So right now we have people from all around the world, even in this talk right now. And I think it's very exciting that we are all part of it. And even we have like different internal motivations as industrialists or academics. We as students, we I think are joined towards the same goal.
You know, even more to reinforce what you're saying, even over the last year, there's been amazing changes globally in quantum. For instance, a company went public, IonQ, listed on NYSE, you know, a very highly regarded exchange. And you have to jump through a lot of hoops to get listed like that. So they must be doing a lot of things right. And companies are getting funded for hundreds of millions of dollars, like PsiQuantum, I think got over $300 million. Now, you know, VCs obviously are far from stupid, so they're not going to give out that kind of money unless there was some realistic chance there was going to be a payoff. So not just from the science point of view, but from the marketplace point of view. there's a lot of attention coming in now. So it's a good time to be involved.
Yeah, and even near me, so I'm based in right around near Cleveland, Ohio right now, since Stanford's virtual. And I heard that the Cleveland Clinic was actually going to be one of the first, or the first like commercial customer for IBM's quantum computers. So I mean, it's actually expanding into use now.
Basically, I mean, if I was the age of the average person on here, it's a great move to be involved because it really bodes well for your future. I think in 3-4 years, it's going to be an amazingly ongoing sector.
Also, it's super interesting. I mean, it's fun to be in this.
That too. It kept my sanity during COVID. I would have gone berserk if I didn't have something to focus on.
Hi, Nathan. Alexei here. Great to hear you. I just want to say, I think you're so, passionate and vigorous that any young person can be jealous of that. So, I think you set a great example for all of us here, and it's great. Basically, I think Logan mentioned IBM, right? So I'm at IBM Quantum now. We see a lot of interest, right? A lot of different clients. I mean, I cannot talk about specific clients, but we do have clients in finance exploring similar approaches to what we heard in the first talk, right? So definitely, what I can add from industry perspective, right? A lot of work is now in exploration. So industry has, I think, like primary kind of player which we see is a large company, such as large, multinational bank or global oil and gas exploration company, right? Which basically has an R&D arm, which is tasked with research in quantum computing as an expansion, right, of high performance computing, AI. So I would say there is a lot of very cool work where it's basically like an extension of the lab, right? What Mert says is it's kind of you're in industry, but you're in a research group, right? So you read papers, you work with smart people, and you explore this. So I think it's the best of the both worlds because you're kind of paid industry wages, right? And kind of global companies provide huge opportunities and interconnections. And at the same time, you're working on this cutting edge problem. Another very interesting phenomena I realize is happening. I've seen the Simons Institute talk by Yuben Tang, and she presented very interesting work. So she kind of dequantized a bunch of algorithms, right? So quantum algorithms pose the question of quantum advantage. However, what might happen is that people start looking at classical, and then they start being inspired by quantum math to actually implement a classical algorithm, which will be faster than the state of the art. And so she actually I think there is like this movement now to dequantize a bunch of things and make classical faster, right? I don't think it takes away from quantum computing, but it shows that all this math deep dive has impact on a lot of different areas. So I would say kind of the best of the both worlds is that you get to kind of learn or relearn all this math, which is very interesting, and then you can kind of expand your mind and apply to different things. So that's kind of my current feedback on the industry connection.
Yeah, thanks, Alexei. As I said, Alexei started this whole organization, and he's right now at IBM. So great perspective from his side. He's been dealing with academics and people from industry for a long time. But yeah, definitely agree. It's fruitful to be in this field in every perspective. So I'm glad that I see that in all of our sessions, I see a very diverse crowd. So thanks, Dmitry, for leading today. For our next event, I think we will keep everyone posted. Thanks all for joining. I'm gonna stop the recording now. If you have anything that you want to discuss, we can keep this going. But otherwise, thanks all for coming.
Thank you so much, Marat. Thanks, guys.